Okay. Um, last class we were talking about the end. We were talking about for loops, and the there are basically two kinds of loops that we have in any type of coding, and they're very similar. And those are the while loops and the for loops. And you can do similar things with either kind of loop. And so we were finishing up here talking about for loops and gave an example here with this piece of code. Let me run it and called it many Zoogs code. We're drawing the Zoog character here, and we're doing it with a for loop. And the for loop, let's find where the for loop begins, right here. And so notice that the difference between each one of these Zoogs is the location in the X direction. Okay, so that's what we have here is we have a for loop, and we begin with X equals 80, and we execute this loop as long as X is less than width, the width of the window. And then each time through the loop, we increment X by 80. So each one of these is 80 over to the right from the previous Zoog. And then what this does is it just redraws Zoog's body. And notice that the variable X here appears in everything that we're drawing. This is all of our Zoog drawing code, that you can see that as we're increasing X, you can see how every element here will get moved to the right as X moves to the right here. Now we could have done the same thing with a while loop. And I'll talk a little bit about that in a few minutes, I hope. Now, let me just mention to everyone again here that I have posted on Moodle the sample final exam. So you should go in and look at that. Now, next week, I will post the real final exam. But for right now, I posted a sample final that you can look at to help you prepare for the real final exam. I still want you to do the homework assignment for next week. In other words, the homework assignment you're doing this week to be turned in on Sunday. I still want you to do that. Okay. And then instead of doing another homework assignment next week, you have the real final exam to do. And you have all week to do it. And I'll give you directions on when I want that turned in. It might be on Saturday that I want you to turn it in. Okay, so that's a little heads up here where we're going. We're almost finished with the course here. And so let me get right into our code for today here. So I'm in lesson 7 here. So let's look at the first example in lesson 7. Okay, now what I'm doing here is talking about how we can define our own function. Now we've been using functions. If we want to draw a line, we use the line function, or a circle, we use the ellipse function, or a square, we use the rectangle function. So we've been using functions here, but we're not limited just to those predefined functions in processing. We can define our own function. And we define a function using a statement like this here. Here I have void draw black circle. Now every function doesn't necessarily have to begin with this void command. And the only thing I've really told you right now is that void means that the function is not producing any output, let's say, to your screen necessarily here. Void. We use the void setup and void draw. Now there are other terms you can use here, but that's just something I haven't really gotten to explain in detail, and I don't want to confuse the lesson by going into what that is. Now notice that this function, which we're calling draw black circle, now notice that the function has open and close parentheses. So that's a characteristic of functions that we use. And in this function, we're using a predefined function, ellipse. So all this function really does is it draws an ellipse that's black, fill is 0. So this is a predefined function, and all it does is draw a circle that's black. So this whole thing going from here to here, this block of code is a function that is called a user-defined function. And then once we add this to our code, we can then call that function from anywhere in the computer program that we write. Okay, but we have to have this function defined in our code listing that we write out. And this will not be put inside void draw. We'll put it outside void draw. But inside void draw, we will call draw black circle. So we might have a statement inside void draw that calls this function, but the function is a block of code that sits outside void draw. You'll see a little bit more of that as we go along and what it means. Let me run this. So you see, I run it and nothing is happening. I'm not getting a black circle. And I'm not getting a black circle because I'm not actually calling this function anywhere in the program. I'm just defining the function, but I'm not calling and executing the function. Okay, so if we want to define a function, we're going to write a set of code, something like this. This will be the name of the function. And don't forget the open close parentheses. Okay, let's go back and continue to see how we use our functions. Okay, now this is calling a function right here. So this code right here, after the function has been defined, here's void draw circle. So here's the definition of our function. Here's our void draw. Remember, void draw is a loop. Like a for loop or a while loop, void draw always executes as a loop. Okay, so if you're executing a block of code that's called void draw, it will loop over and over. Inside void draw, we're drawing our circle. We draw a black circle. Now, here is where we define what draw black circle is. So this function is defined in a program. It's defined outside the block, void draw block. So we have a void setup block here. We have a void draw block, and then we have our user-defined function draw a black circle. Now let me run this code. And here we get our black circle drawn here. Okay, and that's all that this does. Okay, so it's not a particularly useful function. Now we can elaborate and make this more extensive, and which is of course what I want to do. Let me come back, close this. Modularity. Now, I have mentioned a little bit about this before, modularity, and it's a potentially confusing concept. I think that that students studying computer science, it can take them a few mistakes before they start to understand what modularity is about. But we use variables inside of our programs. And the variables typically are defined inside specific blocks of code. Now let me try to explain that with this example. So notice we begin this block of code. We declare variables, x and speed. That's the first thing we're doing here before we even call the void setup function. Now, when we define variables like this right in the beginning, we can use these variables anywhere in our code. So this is a pretty large block of code. So our variables x and speed can be used in any other block of code inside this sketch. Okay, so here we have our void draw right here. So we could use x and speed inside here. Now, you don't see x is not appearing in there. So are we using x in there or not? Well, notice these are three functions: move, bounce, and display. So we have these variables defined here. We have our void setup block. We have our void draw block. And we have three user-defined functions. Move is a user-defined function, and it's defined here in this block of code. Bounce is defined in this block of code, and display is defined in this block of code. Now, in these three functions, we are using x, and at least in some cases, using speed also. So what happens is when we define x and speed right in the beginning, before anything, these are what are called global variables. We can use these variables anywhere in our sketch. And in particular, we're using them in these three user-defined functions. Okay, so notice it's not explicitly being used in void draw, but void draw uses these three functions. Okay, so that's what's going on here. Now, what happens is that if I define the variables right here in the beginning, they're global variables. But if I were to define the variables, let's say inside this function and not up here, they could only be used inside this function. And I could not use x or speed in any of the other functions. So this is what's referred to as modularity, is the region where a function is defined in your code. If you define it in the beginning, you can use it anywhere in the code. But if you're defining it inside a block, it can only be used inside that block. Now, what's really interesting is instead of defining X up here, I could have defined it, let's say, inside move, and I couldn't use it inside bounce. I'd get an error that the function isn't defined. Now, with this block of code here, let's just experiment a little bit. Let me just comment this out. Now if I run, I should get an error. X cannot be resolved. And notice the first time we use X is inside move. And it says X cannot be resolved to a variable. Now we come back up here. Notice we initially set X equal to 0. And we don't use move, bounce, or display until we get inside draw. So I could try defining X here. Integer X equals 0, semicolon. Now this might work. Let's see, because it's defined here, and these three functions aren't used until we get inside draw. Now we're still getting X cannot be resolved to a variable. So that's not working here for us. So if I explicitly used X for something inside here, I'd be okay. But because the functions move, bounce, and display are not defined until we get outside of draw, X doesn't work when we try to use it inside move, bounce, and display. So even though we're calling move, calling bounce, and calling display, defining integer X here doesn't apply when these blocks of code are executed, because these blocks of code are not defined inside of draw. Now, let's try, let me just comment this out then. Now, there are more things that we could do experimenting here. And we could if the function move, bounce, and display, if we left it here, instead of commenting it out, we could use X in the call statement to move. Now, let's see. I could try this, move X, right there. So I'm using X, I'm calling move, and I'm passing this value of X. I could put, and then I have to write X here and see what happens. Now I should still get an error because X won't be passed to bounce or display, but unexpected token X. Okay, so look at that. So it's not quite liking that either. So the range of a function value is something you so when I comment that, computer science students will make several mistakes when they're trying to utilize these global variables, this is exactly, what I was saying is you try doing experiments like this to try to understand what it means. Let me just comment this out and then come back up here. So integer X is defined. notice that would have given me, that should have given me an error actually, because I defined it here, and if it wasn't commenting out here, that means it would have been defined more than once. And I'm trying to think back here in processing. That actually might be okay in processing, but let's try running this now. So this works. This is what the code looks like when we run it. We have our variable x as a global variable defined here. And because it's defined right in the beginning, outside of any code block here, we don't get a problem. Now, let me uncomment this. So I have x up here, and then I also define it up here. So what this is called, if I define it inside a block of code, it's no longer a global variable, but it's called a local variable. And it's telling me here that x is not used inside of draw. This is a warning. So, if you haven't had enough to be confused about with this, I have actually two different variables of x defined. I have the global variable of x here, right there. And then this, because it's defined inside of draw, is a local variable. But it's not used in here anywhere. Look at that. Now, let's just try. And when I get to move, bounce, and display, this is the value of x that's used, not this value. So if that's not confusing, what would be, right? Let me just try something here. Let me call that x equals 20. And it's still working just as it did before. So it turns out that this local variable of x, because I don't actually have a statement in here that uses this value of x, I can make this anything, and it's not changing this code because this code is using this value of x. Let me make this 200. There, now run. And nothing's changed. So here's some things, if you really want to go into this more deeply, you can. And that fellow, the very beginning that I showed you, the guy who has some video tutorials up, the guy who I said is a bit manic, he actually has some discussions of local variables and global variables and functions. And it would be worthwhile if you want to continue going in and trying to use processing to do various things, to go in and look at that and see if he can confuse you even more as to this. Okay, so we have global variables, we have local variables. We can use the same variable name in both cases. Now, what would happen is if we used x inside of draw, this is the value that would be used. Okay, so let me get out of this here. Don't save. Now, the purpose of modularity is you define variables that are only defined within a certain block of code. And it's possible that outside that block, you might do something inadvertently that would change the value. Like initially in that line of code, we had integer x equals 0. If in some block somehow we accidentally had a statement that's at x equals 5 inside a particular block, that wouldn't change the value of x used in other blocks. Only the global value is the value used. So let's see here. Modularity, return type. Okay. Now, we're going to be talking about functions that define values. Now, the functions that we have defined up until this point have always begin with the term void. And what we mean when we, as I said, when we use the term void, is the function is not returning a value to the part of the program that calls the function. So let's see if we can understand that here in this block of code. Okay, so we have void setup, void draw. Now, this right here, float d equals distance. Now down here, we say float distance is equal to this. This is a function. If I put void here, it would be a function that didn't return a value. But when we call this function, it returns a value. And the value that it returns is whatever the value of d is. So we have float distance. And here, these are all the variables that are used inside the function. It uses x1, y1, x2, y2. Okay, so what is this function doing? It's taking the difference between the two values of x here, dx, the difference between the two values of y, dy, and then it's taking the square root of these two values squared. This is basically the Pythagorean theorem. This is how you find the distance between 2 points. That I'm sure you covered this in several math courses. If you have 2 points in the xy plane, how do you find the distance between the points? You use the difference between their x dimension and square it, the difference between their y dimension and square it, then take the square root. So this is what this is doing, returns that value. So it's returning the distance between the point x1, y1, and the point x2, y2. So this function, distance, returns a floating point variable, d. And right up here is when we're calling the function. We're calling the function distance. We're saying float d is the distance between this point and this point. Okay, then we call d, and by executing the function, return this value here into d, and then we use d elsewhere in this block of code inside void draw. So we call the function distance, return the value of d, and then we use d elsewhere in the block of code. So that's not a function that begins with void. In void, we're not returning any values to the calling block of code. But here we're returning a floating point value, d. If we had integer, the function would return an integer value, or we could return a Boolean value, a true-false value. So we could begin not only with float, but with other variable types, saying what kind of variable are we returning when we call the function. So This is a function that returns a value. Here it's returning a floating value. And when we define the function right here inside the block of code draw, so we're not really defining the function. The function's defined down here. We're calling the function here. So I used the wrong term. We're not defining it, we're calling it. Just like we call fill and call ellipse, we're calling distance. Notice that distance, the text on it is not blue, where it's blue here. It's because blue text is for a function built in to processing. Distance is not built in. It's a user-defined function. And if you're not used to doing coding, this idea of modularity and defining functions and variables only being defined within blocks of code, this can be confusing, certainly at first, and sometimes even for a while. And so the only way you clear these things up in your mind is to experiment with them and try using them and seeing what happens. So here's an example of a function that returns a value. Let me run it again. I run it. Now notice that in the function here, notice that the function is defined, or somehow wherever the mouse is, changes the fill value here. When I put the mouse right inside the center of the circle, we get black. And as I move away, the color changes. So you see the distance that we're computing is the distance between the mouse location and the center of the circle. So float D, notice here, width over 2, between that we have this, here's mouse X and mouse Y, width over 2 and height over 2 is the point right here, which is the center of the circle. So we're looking at the distance between the mouse location and the center of the circle. Okay, so that's what we're computing, that distance. We're filling, fill depends on the value of the distance. So if the distance is 0, all three of these terms is 0. So when the distance is 0, we're filling with black. Okay, and then this is defining our ellipse mode to be center and drawing our ellipse. So here's where we're using distance here. Okay, so we compute the distance between the mouse location, the center of the circle, and then use that value to change the color of the fill for the circle. Okay. Let me close this now. There we go. 7.5. All our friend Zug again. Okay, now we have several variables defined, global variables here, which are the variables, most of these I think are used in drawing Zug. And what it is we are defining, notice all the functions we have here. We have float distance, it's a function that we just used. Color, notice that we're defining color here to depend on the value of D. We have float factor is another defined. Factor is a variable that's defined by the constraint. We mentioned the constraint function a lesson or two ago. And we have functions down here. We have jiggle. Void jiggle is a function, but there's no value returned, okay, with this function. So it's void. Void draw Zug color. So here is another function where we're drawing Zug. So background mouse X determines position and speed factor for moving the Zug function. Let's run this program and see what it does. So there's Zug, or centipede Zug. I bring mouse in here. And as soon as the position of the mouse enters, Zug starts to, and then as I move mouse, the rate at which Zug vibrates changes. Now notice the last position in the window was over here, and that's the position which applies to Zug. If I make the last position here, Zug stops vibrating, keeps vibrating, stops vibrating, vibrates, stops. So the position of X here defining Zug's vibration. And that is, where is that here? We'd set up void draw, constrain. We're saying the mouse has to be constrained. Mouse X has to be constrained to a set of values. If you remember that, here's jiggle. So jiggle is determined by the function here, by the value factor, which comes out of this right here, constrain. And then let's look down here. So so this is doing something that's probably not very useful in making Zug jiggle like that, but it depends on the position of the mouse. We either make Zug jiggle faster or slower. Notice here's a random variable. So position of X of Zug is determined by a random variable. And the value of this random variable, this random goes between -1 and 1. So this would be a uniformly distributed random variable between -1 and 1, but we're amplifying it by multiplying it by speed. Okay, and we're jiggling Zug. Now, it's possible for X and Y to go outside the window. We kind of begin to solve that, is it? Well, what should be constraining that might be this term right here, be constraining the values. So I have to go back and review this code in more detail to see what's happening with that. So let's just run it one more time here. So I go over here, make Zug jiggle a lot. Now, because it's random, if we wait there long enough, the Zug would jiggle right over to the boundary of the window. And so constrain might be used to fix the value of Zug so that he doesn't go outside that window. I just don't remember how I set it up there. See, he's starting to get outside the window now. And if we keep on going, he might get further down. Now, if you remember that bomb program I showed you weeks ago, Mara bomb, early on in the beginning of that sketch, we had what was a animation that's supposed to represent leaflets dropping out of an airplane and fluttering down to the ground. And the fluttering property of those leaflets was generated using a random function similar to what we're doing right here with Zoog jiggling. Okay, so things are starting to get more complicated here, and because they're more complicated, we're beyond the scope of things, that can be explained in a short amount of time in the class. And we're really at the point here where if you're really interested in getting better at this and learning this, you have to go into the code. What I do, I'll tell you what I do. I pull up a piece of code like this that maybe somebody else wrote. I actually have to go through it line by line and see how everything's working. And to do that, it can take hours, days, and in some cases even weeks for me to do that, to go through a piece of code line by line, which is why putting in comments is so important. So here's color. You were saying a color based on distance from the mouse. Let's look at that again, as that's what's happening. Notice that the color of Zoog's eyes indeed change depending on the distance to the mouse. So this is why you want to use comments abundantly in a piece of code. And we're at the point where you kind of have to go through the code line by line and even experiment with values to kind of see what's going on. It's like if you're reading something in a book, or you're reading an essay for another course. When you're reading this essay and trying to study it or analyze it for your course, you have to go through it slowly and carefully. You're reading a story written by a famous author. You have to go through it a section at a time to try to understand it. Same thing with computer code. Okay. This, let's see, this is 7.5. 7.6. Now, this is, I'm not actually calling this part of lesson 7. What I'm doing is I mentioned the fact that for loops and while loops are similar. So I wrote a little piece of code here to illustrate that for you. Here I have a for loop. For integer I starts at 0. This loop continues as long as I is less than or equal to 10. Each time through the loop, we increase the value of I by 1. We then take the value of sum, which is initially defined up here. We add I to it, then take this value and put it in as the new value for sum. Then I print out sum. Then I write down here, outside the loop, because the loop goes from here to here. Outside the loop, I define sum to be 0 again. And now I'm doing pretty much the same thing, only this time with a while loop. So I say integer I is equal to 0, where here I said integer I equals 0 right here. You put a space there. It would still run, that was okay. So integer I equals 0, while I is less than or equal to 10, I change the value of I, increase it by 1. I add the value of I to sum, then I print out sum. So here I print out sum here. Here I print out sum here. This is a for loop. This is a while loop. These two pieces of code do almost the same thing. Well, notice there's nothing graphic being produced. But what's happening is the value of sum that I print out is printed down here. So initially sum is 0, then it's 1, and then I goes to 2. I add 2 to 1 to make 3. Then I goes to 3. I add 3 to 3 and get 6. Then I goes to 4. I add 4 to 6 and get 10. So here it's printing out the value of sum as we execute through the for loop. Then it finishes up here at 55. Then I reset sum to be 0, and I have a while loop that does almost the same thing here. We have sum is equal to 1. Notice up here, the first value of sum was 0. Down here, it's 1. So 1, 3, keeps going. Here we started at 0, 1, 3. And then where this first for loop terminated at 55, this second loop terminates at 66. So there's that small difference between what this loop does and what this loop does. Now, it's not fundamentally determined by one being a for loop and one being a while loop. We could have made these values of sum go between 1 and 66 too, or these values of sum go between 0 and 55. But you might want to look at these two loops and see if you can understand why the range of values in the two loops is a little bit different. Whenever I use loops in a piece of code, I often go in and I will actually print out values of the loop variable to make sure the range on the loop is what I expect it to be. So no, these two loops have slightly different ranges. So if it wasn't intended that the ranges be different, you would have to go in and change something in the loops to make the ranges the same. So I'm recommending that you look through this, try to understand what's happening with that. Now, let me go in and try to find the bomb code again and see if I can run it. I think last time I tried to run it, it didn't run for some reason. There, bomb 25. So doesn't want to open it there. Let me here come down here. There. So because the bomb code uses some graphics and sound files, the graphics and sound files have to be located in a folder together with the code that executes. The code that executes here is bomb 25. There we go. So this is long comment explaining it. Now these are all variables or names of things, images. So I'm defining the images right in the beginning where I define variable values. So I'm telling processing. I haven't gone through this, you'd have to go in and research online to see what some of these things mean, because we haven't quite done enough in processing to fully understand this, but these, you should understand that I'm defining variables right here in the beginning of the program. So these would be global variables. So this is a pretty long code, and I'll tell you that it actually took a while for Mara and I to work through this. What we did, and we didn't jump in and start doing a complicated piece of code to begin with. Okay, I think we actually began trying to figure out how to pull in the photo of Harry Truman and play the sound file of Harry Truman. So we started off doing something simple. And then every time we went into the code, we added a little bit more to it and a little bit more to it. So we didn't start out trying to just write this huge complicated piece of code from scratch. This was a several weeks project that we did, adding a little bit to it at a time. Let me just run this.
The world will note that the first atomic bomb was dropped on Hiroshima, a military base. We won the race of discovery against the Germans. We have used it in order to shorten the agony of war, in order to save the lives of thousands and thousands of young Americans. We shall continue to use it until we completely destroy Japan's power to make war.
Okay, so that was just the first part of the program. All we wanted to do was do that. Then we decided, well, maybe we can add a graphic. So we had the sound of the plane. Then we had to figure out how to draw the plane. There's the fluttering leaflets. Then we had to have the plane come across again, drop the bomb. Notice that the size of the graphic of the plane changes. Then we had to figure out how to do this, where we changed the text as the explosion expanded. Then we added some more text like you would do a PowerPoint presentation. Okay, so each step of this program, we went through and we did one thing. We got that one thing working right. Then we decided, well, we learned a lot doing that one thing. Can we add something else to it? And so we built this thing up very slowly over several weeks, actually. And you can see there, once we figured out how to do the sound file of Harry Truman speaking about the atom bomb, then we think, well, we know how to do sound files. So can we add some other sound files to do other things, like the music and the sound of the airplane and so on? And we added that. The fluttering of the leaflets we did with a random variable, like we did with the jiggling Zug. And so I tell you that, whenever you get a piece of software for your computing, you have, let's say, version 1 of the software, and 1.0. And then the people who write the software, as they get better at this, they start adding a little bit more things, and you get version 1.1 and 1.2, 1.3, where they're correcting errors that they made in the software that they didn't correct the first time they released the software. So fortunately, unfortunately, writing a piece of software can go on for a long time. And you slightly expand it and make it more complicated each time through. I'm not really aware of anyone who sits down and first time through writes an incredibly complicated piece of software. You build it up a little bit at a time, just like when you're writing a paragraph, writing a story, you build it up a little bit at a time. And then when it isn't quite right, you go back and try to change some things. And you begin to see there are things that maybe you didn't have quite right when you go back and change them, such as the range for a function. Is it or a variable? Is it a global variable or not? Does the function return a value? What kind of value does it return or not? And then as you are slowly write more and more programs, as a programmer, you begin to build up sort of a library of your own, of programs that you yourself have written. And then you have those stored away. And then later on, you're writing a new piece of software for something new. And you think, oh, I wrote a piece of code that jiggles Zoog. Maybe I can modify that to flutter a leaflet dropping. So you build up this library of code that you can go back and pull out and use. So it's the writing code, in essence, you're building up a portfolio. You guys should be familiar with portfolios. As you do more things in comms and media, you're building up a portfolio of things that you've done. You have access to that library of things that you've done that you can now go back and use to do more complicated things. So writing code is very similar. My youngest son, who's majoring in game design, computer game design, as he's going through his classes, in his classes he has projects, and he's building up a portfolio of games. Okay, and just like an artist would have a portfolio. And then when he applies to graduate school or for a job, he can make reference to items in that portfolio to show people things that he has done. And so writing code is very similar to that. You don't try to do something super complicated at first. You do simple things, one at a time. And then you gradually learn how to do those simple things. Then you can pull together 2 or 3 simple things to make something that's a little bit more complicated. So that's how this bomb program was done. Now, one thing that we didn't do, that in fact most computer programmers don't do, especially the people who work for the big software companies like Microsoft or whatever, in that you begin writing a piece of code and you start off with simple things. As you're going through, you find little mistakes. You put in what are called diagnostic checks. In other words, you might do print statements to print out values of variables where you don't seem to be getting the right values when you run your code. So then you figure out the mistake. Now what happens is, in that code, you're writing code for Microsoft, people don't go back in and they don't remove those diagnostic printouts. They just comment them out. So the final piece of code that actually gets marketed, let's say for Microsoft Word or PowerPoint, has all of those diagnostic printouts in it that have been commented out. They never went back and deleted them. Why? Because they didn't want to take the time to do that and potentially make some mistakes in doing that. So they left it all in there. So typically the final piece of code that gets sold to the public sort of has this record of all of their debugging process in terms of these commented out printout statements. So it's, writing computer code can be a long and sloppy process. Sometimes people find a mistake and they correct the mistake, but not in the most efficient way. It's kind of a crude correction. May not be the most efficient way of doing it, but it works. So they don't go back to try to find the better way. They leave the crude correction in there and go with that. So this idea that you might have of computer people somehow being exact and precise is not true. And so let's say we've got, you have the homework, you just turned in a homework. You have one more homework I want you to turn in for next Sunday. In addition to that homework, I posted a sample final. You don't have to turn in the sample final, but it's to help you prepare for the actual final, which I will post online for next week. So there's some extra things in there for this week. I'm sorry about that. But us professors were cruel and heartless. And something else you'll have to tell me if you found it to be true. An observation that I've made is I think as we put these courses online, the online courses frequently have more work to do than you would have had in the in-class courses. That's sort of a general observation I've made across several universities and several courses. I don't know if you found that to be true. So I'd be interested in knowing if any of you have found it to be true that your online courses tend to have a little bit more work to them. Anybody want to comment?
Yeah, hi, sir.
Yeah.
Yeah, I found it really like we are having more to do here, like online, than we used to do on campus. I also find it like this, like more works online than offline.
Yes. I actually think I'm a bit guilty of that too. And I'm aware of it. And I'm trying to figure out how to go back and, how to change that, because the online courses are more work for the students and they're more work for the faculty in general. I know I put a lot more time in with the online course because if you noticed, I've pre-recorded videos. And then in addition to that, I do these in-class videos. And I would not have done that for an in-class course, right? The only thing I would have done for an in-class course is done my classroom presentations when I wouldn't have done a lot in addition to that. But somehow for the online course, I've pre-recorded videos and I do the classroom presentations. So it's extra work. So it's like I'm still getting up early in the morning to do the classroom presentations, even though I did the pre-recorded videos. Now, maybe all the professors aren't doing that, but I still think that they are asking you to do more with the online courses. And I think we need to go in and modify that so it's not quite as so much work for the online classes. As I think over the years, actually, since when I was a student, I actually think that university work has become more demanding since I was a student. I think courses are asking you to do more now. And now with this shift to online, I think there's a really significant jump in that. And and like I said, I've noticed to be true across universities. It's true in several, and in fact, it's almost every university class that I've seen. I think the online courses are asking the students to do more work, and the professors are doing more work. So, and not only are they giving you guys more work, but they're stupidly making more work for themselves. That certainly, I think that's a problem, and somehow we need to figure out a way of addressing that. And but part of it, I know with me, I want to make sure that I'm covering all the topics that I want to cover. And when I'm posting online videos, I can make sure and do that. If for some reason I fall behind in the classroom, I may not go in and do extra classes to fill in things that were missed. That's one thing that's happening. But in any case, I'm done with the class today. I'll come back in on Thursday. And so you might want to look over that practice exam and see if you have any questions and ask those questions on Thursday. I'll tell you what, I'm not going to prepare anything new to talk about on Thursday. I'll just come on, we'll look at the practice exam and, generally talk about whatever things might be bothering you over the course. Next week is the final. It's a take-home final that lasts all week. Turn in the final before the beginning of exam week. So then you don't have to worry about this course during exam week. Okay, so I'm done for today.
Thank you. Have a nice day.
I wanted to ask, the practice exam is on Moodle, right?
Yes, I put it on Moodle. And if
Okay.
for some reason you don't see it there, email me and let me know and I'll fix it. So the practice exam is on Moodle. Okay,
Okay, thank you.
sure.
Have a
Bye-bye.
good day.
And also,
Goodbye.
do we have to turn in the practice as well?
No,
Or
you
is
don't.
it just for us?
It's just for you. You don't have to turn in the practice.
Okay, thank you.
Sure.